Hi, everyone. Welcome back on our second day of the summer school. And I hope you all had a great day yesterday. And I'm Yan Jia from Physics Department, and I will be hosting the session today. So our first speaker today is Professor Eun-Ah Kim from Cornell University, and she will continue her presentation, second part of her presentation on the fractionalization due to the orbital geometric frustration. So let's welcome Professor Eun-Ah Kim to the stage.
Thank you for the introduction, and happy to be here. In case you are wondering how to say my name, ignore E, then it becomes easier. Just say Eun-Ah, that's pretty good. All right, so I want to continue my talk, talking about orbital geometric frustration. And advertisement yesterday was today we're going to see really pretty things, exponents that's calculated computationally coming out of analytic calculation. Doesn't happen every day, so I'm really in love with this beauty of how things worked out. But before I go into the part that was promised, let me just quickly recap what we were discussing yesterday. So to step back, the idea was that when we think about correlated system, route to fractionalization that's very much well established and very much loved is that of fractional quantum Hall effect, where you start from free electron. This is a quantum mechanics exercise homework problem. You get Landau levels. You put free electron in 2-deg. You get flat dispersion and the gap. And then you think about what happens if I partially fill it without interaction. I should have a gapless system because I have this distance to go and I'm just moving around here. But once I put the interaction, you find that once you put the interaction, you get Laughlin state. And there are different ways to see this, but it's well established and very much loved by the community. And it's first thing that we try when we see some new fractional phenomena where you think you have time reversal symmetry breaking and you see some plateaus in the Hall conductance. This is how you approach it. But what I wanted to think about, what I invited you to think about is a different paradigm where you start from largely degenerate, extensively degenerate states that you get just because you have interaction. So if I have a many-body spectrum that looks like this, I have a ground state that is very degenerate. It's possible that in such a setting, you can get fractionalization from the get-go. And then you can start asking, so what happens if I introduce fluctuation, quantum fluctuation? So it's a different kind of framework. And where can this occur? I argued that it's now pretty well established if you have twisted bilayer graphene without needing to tune to magic angle, just because of having a moire system where alignment between two layers occur at these bright areas that seemingly form a triangular lattice, but you cannot make Barnier orbitals or position bases where you can start thinking about interactions out of triangular lattice and match the band structure features. And instead, what you should really think about is this fidget spinner. So now I have my weights of the wave function forming what looks like a triangular lattice, but the center of this wave function that really determines where the whole object is living actually sits on sides of the hexagonal lattice. And such extended object, to think about the Hamiltonian of this extended object is cumbersome and painful. It's complex and rich when you are in a positive mood. It's annoying when you're tired. So people kind of moved on from this real space picture when the community was really interested in integer filling and correlated insulator phenomena at integer filling. But my collaborators and I thought about fractional filling, and we realized that 1/3 filling, everything becomes very simple. Well, they would want to repel each other, not just when all 3 lobes are overlapping, but you really don't want any of the lobes to overlap, which results in our trimer model, where we start thinking about tiling of these orbitals. And for illustration purposes, we're going to represent them. We represented them with triangles. And you can see that because of the shape, you can think about polarization associated with these orbitals if they are all facing one way, or rather if they are all occupying AB site or BA site. That's one order parameter. And the arrangements of them forming sort of a crystalline state or incompressible state can also give additional order parameter. So this is where we got to yesterday. And we saw that this notion of no touching condition that is very intuitive once you have these toys, the fidget spinners, you can start laying them out and you realize that, well, if I don't want them to touch, that means once I occupy this BA site, I don't want any of these sites on the hexagon to be occupied. I don't want any of these sites to be occupied, and I don't want any of these sites to be occupied. So all the areas that I grayed out are the regions that are forbidden. And that condition can be compactly written in terms of this cluster charging Hamiltonian. So this Hamiltonian says for each hexagon on my BA-AB honeycomb lattice or hexagonal lattice, for each hexagon, I don't want more than one site occupied. And this is a term that is trying to control not just on-site occupation, but nearest neighbor occupation, second neighbor occupation, and third neighbor occupation. So it's a sort of a long-range interaction, but it's not as long-tailed as a Coulomb interaction, but it's still more structured than on-site interaction, which is really responsible for a lot of the richness that we are seeing. Now, this model, I said yesterday, is exactly solvable using Bethe ansatz. And it was found that such a model would have extensively degenerate ground state, where your entropy goes like L squared in a 2D system. And that entropy was explicitly calculated with Bethe ansatz. Now, once you add the next leading interaction term, that is one way to perturb away from this extensively degenerate state, and that leads to different ordered phases. Interestingly, this next leading term is, the sign of this term is not fixed. It can be positive when it is dominated by Coulomb, or it can be negative when it is dominated by Hund's coupling. That means it is reasonable to consider that under different circumstances, one or the other might be a leading ordered state where the degeneracy will be necessarily reduced compared to extensive degeneracy at this point of U4 equal to 0, where √3 by √3 has just threefold degeneracy associated with the registry, but the brick wall state turns out to have additional residual degeneracy that is sub-extensive that grows like L. So this is where we ended up yesterday. And the promise, the advertisement was that we will add another axis here, that's temperature, and we'll study what is the correlation function of the fractionally charged objects that we can think about, the monomers, and what is the nature of this point, and learn what is the extent of the phase space that this point can control. Okay, any questions at this point? Yes?
The same phase diagram producible without quantum fluctuation.
This is all without quantum fluctuation at the moment. Yeah. I'll get to quantum fluctuation towards the end. All right, so we wanted to ask, Well, so we have this extensive degeneracy, and we know these monomers are fractionally charged. We can make a monomer by considering different arrangements of these tiles and effectively localize 1/3 charge. But what you cannot get out of beta ansatz easily is correlation function. Correlation functions are very hard to calculate. So what we decided to do was to study the nature of this point and the extent to which it has support at finite temperature using Monte Carlo. And so this part of what I'm going to talk about today really wouldn't have been possible without Kevin being really resourceful and creative and never giving up on this rather challenging Monte Carlo simulation, and then being very creative in figuring out how to think about our results. And all of this was with a great deal of help and encouragement and insight from Roderick, who's been our collaborator. So why is Monte Carlo hard? Well, Monte Carlo is either straightforward, then it's given as a homework problem, or near impossible when you have sign problem. But in between, when Monte Carlo is doable, it can be still hard if there are many configurations that you have to explore in order to be in equilibrium. And in our case, this extensive degeneracy, in order to access different configurations in our degenerate manifold, we couldn't access them through a local move. I showed you that there is this notion of a flip line. You take one legal configuration and you can flip along a line, then you arrive at another legal configuration. But you cannot just flip one triangle or just pop one electron. You have to go along a line. So it requires extensive, large-scale, a global update. So we implemented two global update algorithms. The first is the pocket algorithm explored by these two groups that independently. And the other was this global flip line update. This pocket algorithm makes use of the fact that if I have one configuration, another configuration must be obtainable through mirror symmetry. And this pocket algorithm is rejection-free and enjoys short autocorrelation time. But unfortunately, it does not give us all the updates that we need. So then Kevin added additional global flip line update, which is sort of a generalized version of directed worm algorithm by Sandvik and Messner. This is not exactly rejection-free when we have the perturbation away from the exactly solvable point, but it still allowed us to reach equilibrium in many cases that we considered. So with these Monte Carlo approaches, we arrive at this phase diagram. And this is where I ended yesterday's talk. So this phase diagram is obtained through Monte Carlo, and we studied different system sizes to do finite size scaling and use Binder cumulants to identify the critical points, TC, and the nature of transition. This is the point of interest that's exactly solvable. And this blue shade is showing that when we go away from the 0 temperature, that exactly solvable limit, up to some range in the temperature scale, we see the phenomena that is the correlation function behaving more or less the same way as it does at the 0 temperature limit. So in that sense, that this region of phase space is where you can access this 0 temperature physics within the length scale that is a correlation length scale. That length scale depends on temperature, obviously. But at about 10 Kelvin, the length scale reaches to about 10 Moray lattice constant, which is pretty large. Now, these are the order phases that we had already identified. This is √3 by √3. This is the brick wall phase. But by doing this Monte Carlo simulation, we also found an additional phase here, which we called polar fluid. And you can understand why having an additional phase is possible because you can recognize that this √3/√3 phase breaks two distinct symmetries. One is the sublattice symmetry, or having polarization, where everybody's pointing up or down. That order parameter is non-zero. And then the other is translational symmetry breaking. So when you restore one, that is, you get translational symmetry, but not the other, that is first transition. And when you restore the second, the sublattice symmetry, that is the second transition. These two transition lines meet here at a tricritical point, and then below that level of J4, we have a direct transition. So now, for next while, I am going to discuss how we identify the nature of transition at each of these phase boundaries, and what we learned about the nature of these phases, but using the correlation functions that we could calculate using Monte Carlo. Let's start with a small J4 right here. So this is the first place we're going to start with. The order parameter here is the Fourier component of the density, because if I look at the centers of these orbitals, the unit cell has been tripled, which makes sense because I'm considering 1/3 filling. And this order parameter you can get by just taking the Fourier transform of density. And if I come down in temperature, starting from disorder phase, trying to cool down to order phase, we can look at the Binder cumulant, which is this is a fourth order cumulant of energy as we look at different system sizes. Now, you can see that as I increase the system size, the value of the Binder cumulant is moving. However, it is not reaching 2/3, which is what it should be if it were to be continuous transition. So this is the first evidence against this being a continuous transition. Now, there being multiple symmetries being broken, I wouldn't normally expect continuous transition anyway, but if it was continuous, it would have to be something rather unusual. However, this is evidence that is against the continuous transition. Moreover, looking at the energy histogram at this critical temperature scale, when we look at how many configurations that you obtain with Monte Carlo are within some energy window, you see this double peak structure, which is characteristic of first order transition. So based on these studies, we established this is a first order transition. But nevertheless, we can ask what is the nature of this phase, especially because we have identified yesterday that this fractional charge bound at the point where these domain walls meet is 1/3 of electron charge. And this fractional charge cannot move. So in the sense that it is not movable, it is fractonic in the language of fracton physics. Now, we find at this √3/√3 order state, this correlation function of these monomers quickly decay, which means if I could make them be apart, it would be a fracton that is not moving. But this correlation function really says that it's confined and it's never going to want to be apart. So that's kind of disappointing. But then later, we'll see how one can perturb our model, this cluster charging model, with additional terms to relieve this confinement and make this fracton visible. At least here we are seeing that this fracton is confined, therefore not really something that we can talk about at this point. Now we go up, move to the right, and we can study these two transitions. Once again, we look at the fourth order Binder cumulant of energy. And what we find is that this transition and this transition are both approaching the cumulant value of 2/3, which is what you expect from continuous transition. So now we are seeing that these two transitions are continuous. Then we are invited to look at the exponents. So to look at the exponent, and we can identify the tricritical point. Now to look at the exponent, we calculate the susceptibility. So here, because what is disappearing is polarization, we look at the polarization susceptibility, and this beautiful scaling collapse gives us this set of exponents. Down here, as we develop the charge order, we once again look at the susceptibility and a scaling collapse, and that yields these set of exponents. And interestingly, these are actually known exponents that's associated with three-state Potts model. So that was sort of interesting finding that this is this phase transition that we can recognize where there's number 3 floating around, but it is not obvious that this should be a Potts model universality class, but that's what we found from the calculations. So that's so much to do with the positive J4 side of the phase diagram. Now for the negative J4 side, we get this brick wall phase, and we said yesterday that the brick wall phase would have these monomers that are bound to the domain wall between 2 different ways of the brick wall leaning. So it can lean one way or the other, which gives us that sub-extensive degeneracy. But having the sub-extensive degeneracy also means we can bind these fractional charge at the domain walls. And what was kind of cool about these objects was that they could only move along one direction. So there was a sub-dimensional mobility. And at least in the direction that they could move, they were also deconfined. So it's got the right characteristics to be called line-on. And we wanted to look at the correlation function to confirm that it is indeed deconfined. So this is the correlation function of the this dimer monomer correlation function. And along this line, if I plot it as a function of separation, you see that it sort of saturates to a finite number, confirming that they behave as a deconfined line-ons. So that's on this side. Now, when it comes to the nature of transition, this transition was glassy, probably precisely because it is easy to have this line-ons around, and they define these domain walls, and we couldn't get a long-range order pulling down from the disordered configuration. It would require yet another type of update, which we haven't quite figured out at this point. But so we estimated these TCs by starting from order phase and finding out when they become not favorable, which only gives sort of an upper bound and rough estimate. But these glassy physics will be interesting thing to further study. So now I've covered 2 sides of the phase diagram where the perturbation have ordered our extensive degenerate ground state. And now we can move on to the most interesting part having to do with the trimer liquid. So the algebraic trimer liquid. Here, when we study the correlation function of monomers, this is a monomer-monomer correlation function, log-log plot, using the scaled variable to compare different system sizes. And what you see is that there is a well-defined, clear power law decay in this monomer correlation, up to the length scale that is dependent on the temperature. And at U scale of 10 millielectron volts, this would be sort of a sizable, observable kind of length scale. So that's really interesting. So we decided to look further into this phase. If we put one trimer hole without hole doping in, sort of removing an electron or a trimer, we wouldn't be able to see any monomer at 0 temperature, because you would have this flat configuration and that's incompressible. So in order to study monomer-monomer correlation at 0 temperature, we remove one hole. And this is the result. And this is like at best very boring. It's isotropic correlation function, monomer structure factor, and all you see is the lattice peaks. So it's boring, but maybe that is consistent with this monomers forming sort of a liquid state. Now, what about the exponent? As I showed you earlier, there is this power law decay. But then we added another trimer and another trimer, so tried adding 3 trimers. And now this is what we find. So we're still looking at the monomer correlation function. So this is the sort of raw data. When we look at monomer correlation function as a function of separation, it kind of goes up and down, right? Depending on the monomer pair distance. But the pair distance is not just the distance, because as we move the monomers, we're moving which sublattice it is occupying. So we can organize this correlation function into 2 distinct power laws. So here's one power law, minus 0.24417, which looks possibly close to minus 0.25. And there's another power law here that is positive, 0.471, which looks possibly close to 0.5. Now, these are 2 different power law behaviors we found for the correlation function of the one object that is a monomer, and that is rather unusual. And this is what we then set out to figure out what's going on. Let's first look at the trimer-trimer correlation function, or this would be like electron-electron correlation, or what you would get from X-ray. Now, this is the density-density structure factor in free space. And what you're finding here is there is this curious pinch point structure. And there is one pinch point here at K, and there's another pinch point at K prime. What does the pinch point tell you? Does anybody know what the pinch point tells you? Okay, this pinch point tells us that these density operators that we're looking at the correlation function of behaves kind of like electric field in good old E&M. How does that work? Gauss's law. So Gauss's law in momentum space looks like this. That's divergence of E equal to 0 written in momentum space. This means electric field following the Gauss's law without any charge at anywhere in the vacuum has to satisfy, this is purely transverse, has to satisfy correlation function of this form. So you can see that there will have to be vanishing points, and there has to be very anisotropic pinch point-like structure. So having a pinch point tells you that there is some sort of Gauss law in action. There is some conservation law specifically of the Gauss law type. Having 2 of them means that there are 2 types of Gauss law in action. The correlation function of trimers show exponent that is going like 1 over r squared. So now there are 3 exponents that we want to target. We have 2 types of monomer exponents, power law, and we have trimer-trimer exponent. And these are things that I would like to, these are the answers that, if possible, I would like to get to with some insightful treatment of the problem. So that gets me to effective field theory. The first step in deriving the effective field theory for our trimer model is to map the trimer problem to 3 interpenetrating dimer models. So here is the mapping. Gray triangles are our trimers. And we are going to think about this trimer having to do with dimer configurations, dimer covering of 1 hexagonal lattice, that's the blue lattice here, and another hexagonal lattice, that's the green lattice, and 3rd hexagonal lattice, that's the red lattice. So I'm thinking about 3 interpenetrating hexagonal lattices. For each of them, if you can kind of squint your eyes and look at just one color, let's say red here, you can see that these red dimer configurations that I've written down based on the trimer configuration. That is, I take this trimer configuration, and whenever my triangle, my trimer, my orbital touches a side of a hexagon, I put a dimer there, right? So these dimer configurations satisfy the classic dimer constraint. That is, every lattice site has to be touched by one dimer and only one dimer. So we can see that there are 3 dimer models that we can map our one trimer model into, but they cannot be independent because wherever there is a trimer, all 3 dimer configurations have to be conjoined. So there is a constraint that combines the 3 models, which means there can only be 2 independent degrees of freedom. Now, what about the monomers that we are interested in, the fractionalized objects of my interest? So here we place 3 monomers, right? So having placed monomer I place the monomers from the trimer model as we were placing monomers by flipping the triangles around. But now I look at it from the coupled dimer model perspective. I realize that this monomer is violating the dimer constraint on the green lattice and also on the blue lattice. So this monomer of my trimer model is a monomer on the green dimer model, and simultaneously it is a monomer on the blue dimer model. This one is a monomer on the red dimer model, and simultaneously a monomer on the green dimer model. Now, hexagonal lattice has 2 sublattice sites, and placing monomers on an individual hexagonal lattice dimer model, we can assign sign to the charge of these monomers or vorticity of the monomers, which I'll get to in a minute about how you get the vorticity. But I can, for now, keep track of is this monomer placed on the A sublattice or B sublattice of my hexagonal lattice, and that allows me to assign, okay, this monomer is a violation on the blue and green, and A for blue and B for green. So this white black is giving that notation. And this is a monomer that is green-red. Now you can kind of see that how there might be 2 different types of correlation. These are same types of monomers, and these are different types of monomers. So we are starting to see, even without doing any calculation, that what we've observed in simulation might be plausible. And in order to actually carry out the calculation and get to our exponents that we are targeting, we need to make a mapping to the effective field theory using height model mapping. This was first sort of written down in a very intuitive and tangible way by Chris Henley in this paper. So what you do here is you're going to pick, say, A or B sublattice site, and each time you are going to place this height variable on the centers of the placket, which is a dual lattice of a hexagon. And each time I go around the sublattice site A, I will move in a clockwise fashion in this case. I will pick one side to be 0, and if I don't cross a dimer, I go down by -1. If I cross a dimer, I go up by 2. So here you can see I start from 0, down by 1, and I'm crossing a dimer, up by 2, no dimer, down by 1, and I come back to 0. So this assignment can be made in a consistent way, and it's a 2-to-1 mapping. But if I pick only one sublattice, I can uniquely specify the height field configurations. Now, the fact that I came back to 0, circling around, means the gradient of this height field satisfies the Stokes law. There is curl freeness to this gradient. Of course, if I have a gradient field, curl of gradient is 0. So you can see that this is a consistent way of assigning a field. And I can take the continuum limit this way if I don't have any monomers. So now I have these height variables, and as my dimer covering can be mapped to height going up and down, it is designed such that, and it was found, the highest entropy is a state where it is asymptotically flat. So with respect to that flat configuration, the effective field theory can be sort of conjectured to be Gaussian, and then rigorously checked that the resulting correlation function matches what you can get with the methods like Gaussian methods to figure out what the stiffness is. Now, once you get to this point, you get to the wonderful sort of set of literature that sometimes go as Coulomb gas, solid on solid, XY model. It's all the same thing. They give you this beautiful log. So this correlation function of this height variable is logarithmic in 2D. And my stiffness constant will enter here. What good does that do to me? Well, I can continue on thinking about monomer field because I want to get to my monomer correlation exponent. The height field mapping, this assignment was fine as long as I have dimer configuration and no violation of the dimer constraint. But once I have a monomer, you can imagine, so if I don't have this dimer here, that would be a monomer right on this side. Let's imagine I don't have a monomer, I ran out of time. Dimer here, then what you would have is you go down, and once again down instead of up. So you'll have a winding. So monomers are vortices, and depending on whether you have a monomer at A site or B site, your vorticity will be plus or minus 3. So now how do we do the field theory when you have this kind of singular things happening? Well, what we were taught by all the developments in STEPMEG around XY model, et cetera, in the golden days is that you have to think about slow variables, spin wave often called, and the variable that takes care of this winding. So in terms of the slow variable, we will still have a Gaussian theory, but this new variable that is handling the fact that you have this dilute set of monomers will allow me to integrate out this slow variable, which is the Gaussian, and arrive at this form where my curl or my vortices are once again interacting through a log, which is the Coulomb Coulomb interaction in 2D. So we see that the vortices interact logarithmically, but the K, the stiffness, is now in the numerator. One last step to get to my exponent. Doing this dual transformation with vector algebra is fine, and it's very tangible, but it gets cumbersome when you have many different colors to keep track of. So it is more convenient to think about the duality transformation. Now I'm going to think of path integral of theta, a dual variable instead of the original variable. And what you can notice is if I just consider, for the moment, a new boson whose action is given in this form, where K is in the denominator, the correlation function of these data would be, once again, log. But writing a vertex operator of this form would allow me to get a correlation function between these two objects interacting like a log and give me the correlation in this way. So now this tells me that I can either think of my original variable and integrate out through this Hubbard-Stratonovich transformation, or I can start with a dual variable. So this is how we can think about monomer in terms of dual variables, and that's how we're going to derive the exponents that we observed in numerics. One last thing we need to do is to think about dimer field. The dimer field here is associated with change of the height field. So here the dimer field is assigning that my height field is rising. Here the absence of dimer field says my height field is sinking. However, these three configurations are equivalent, only related by lattice transformation. But when I consider these three different configurations, height field changed by 3. So in this mapping, there has to be periodicity in the height field. The dimer field is sort of most intuitively related to the gradient, but it has to be periodic in period of 3. And the way you can accomplish that is to consider the dimer field as being related to the gradient of the original boson as well as the exponential operator. And then you can get the dimer-dimer correlation function to be 1 over r squared. Now that already sounds like one of the exponents that we looked at. If you remember, there was 1 over r squared, there was 1 over r to the 4th, 1/4, and there was r to 1/2. Those are 3 exponents we are after. So how do we get to the trimer model? This is the trimer model. We have three high fields, R, G, and B. I usually don't use RGB colors, but in this case, it just seemed most natural to use RGB. Now, I'm showing you only 2 fields instead of 3 because they are coupled, so you only have 2 independent degrees of freedom. I can choose RG or RB, but then I demand, because the trimer insists that some of the 3 gradients must be vanishing. That is, this is not like dimer where you add 2 things and you get to vacuum. You need sum of 3 to vanish. So the action that I obtain, whether I obtain in terms of RNG or RNB, should be consistent with that constraint. And that fixes the stiffness. The first stiffness will be fixed by saying that each of them behave like a usual hexagonal lattice dimer model, that is pi over 9. And the second stiffness can be fixed by demanding the symmetry upon permutation between the 3 colors. So now we have field theory. It is a little richer than the original field theory, but by just a little bit, and as far as calculation is concerned, because this is still quadratic and Gaussian. Most importantly, obviously, you can diagonalize it. So now you arrive at 2 orthogonal bosons, what we call phi of t and phi of r. And now here you have just 2 copies, and you can, go do your calculations, something that is very enjoyable because you can actually do it. So power loss, do we get the power loss that we are after? The trimer correlation function, the trimers are made up of dimers, 3 dimers. So R dimer, G dimer, and B dimer. So we write them all down and try to calculate their correlation function. But we remember that we are really interested in the long distance phenomena. And you can find that it is really governed by 1 over r squared, just because that's how each dimer behaves. Okay, that's one easy thing. The next one is monomer-monomer correlation. Now we have 3 different types of monomers, whether it involves RG, RB, and GB. So this R bar means it is a monomer violating B and G, etc. You cannot have just 2 monomers. You have to have at least 3. So we place one at a far distance and look at the correlation function between these 2 pair of monomers. Each monomer can be written in terms of these dual variables. Now we have 2 dual variables because we have 2 dual bosons. But then the rest is just a very simple correlation function evaluation, because these data are they have log correlation. And from the log correlation of data variables, you can work out the exponents. And there it is, our first success. There is r to minus 1/4. That was one of the exponents that we were observing. And we can also look at the correlation between same type of monomers. And going through the similar kind of calculation, you can work it out to be going as r to the 1/2. So now let's check with how these results of calculation compare to our Monte Carlo results. So this is the Monte Carlo result. So this is our field theory prediction for this exponent would be minus 0.25. Now this is finite size system, and the monomers can be only so far away. So this is pretty close. And the other exponent was 0.5, which is also pretty close to what we're observing. So we feel we were very excited to be able to say, not only we can explain why there are 2 types of power law behaviors, the sign is the sign of the two power laws having to do with vortex-vortex or vortex-anti-vortex attracting or repelling, but even the values of the exponents. So now, what does this all mean? I've got these power laws and exponents. What does that mean? If we step back and think about what it means and how does it fit in with things that people have been interested in before us, what we are finding is that our monomers are bionic, meaning these monomers are charged under two coupled Yuon gauge theories. Those are my bosons, phi T and phi R. And the monomers carry the charges of these two bosons. This kind of setting of having the fractionalized objects being charged under two bosons instead of just one usual charge, electricity and magnetism, it's kind of like having two types of photons, was previously considered in the context of spin ice and in the context of p orbital in also sort of a frustrated geometry setting. But neither of these cases, they were both 3D, and when they were thinking about this, it was sort of out of curiosity, thinking about what could one think about that would be new and interesting. What we kind of found ourselves in this interesting territory as we were pursuing what would it mean for our orbitals to have the shape they have. Okay, so that kind of concludes where we got to in exploring the strong coupling limit or classical physics of our trimers and monomers. And that's all interesting. But people always ask, what about the quantum effect? Like, will it survive quantum effects? Do you get something cool if you consider quantum effects? And that's the kind of question that's easy to ask and hard to answer. And that's why people ask, because it's easy to ask. Well, we were curious about this too, and we try to see what we can do about that. We have two different efforts ongoing, trying to understand quantum effects. And neither are easy, but we have some preliminary results. And I'm going to just show you a little flavor of where we are. Okay, so why is it not easy? Well, anybody who knows a little bit about the dimer models know you can go from the dimer covering, which is the setback problem, to quantum dimer model by thinking about these resonating moves. So you would ask, well, what can we make resonating moves out of our trimers? So how does the resonating move work? Resonating move is a local move that you can arrive at another legal configuration. So what you want to think about is that how do I arrange things so that within a finite number of local move, I arrive at another legal configuration. We know how to arrive at another legal configuration doing a very extensive move. That was like this flip line. But if we think about this flipping as a hopping, because flipping would get me from say this side to this side, if I flip this triangle, so it's a nearest neighbor hopping. We want to know what can I get out of this sort of nearest neighbor hopping. We need to stay within the degenerate manifold, so we want to respect all our constraints. So the first thing is that we want to maintain that in the plaquette, the occupation number does not change. So here is a local move that would at least keep the numbers the same. Plus means adding a particle, minus means subtracting a particle. So you add, subtract, you will not change the number of particles. But this operator, it's a sort of our version of a local move, would annihilate our configuration because it is subtracting 3 particles from a plaquette, whereas our filling, which is not part of the Hamiltonian, but the filling dictates our constraint. Our filling was 1 particle per hexagon. So, this immediately told us that life is not going to be a walk in a park. But then it's tough. So she kept at it, and she found, okay, let me build it out. How far do I have to go to be able to get back to my legal configuration? And what she found is that if you build an operator which we call Lemnis gate operator, because it looks like this like infinity sign or number 8 lying sideways. This is the smallest operator. Now, this is a really big object. If you see that this involves nearest neighbor hopping, so like many, many sites, 8th ordering hopping or something crazy like that. So, this is kind of where we arrived at and realized that, gosh, trying to study what this would mean for fermions is going to be really hard. So then what we started to do was to ask 2 different questions. First question that we are asking is, well, if fermions are hard, can we think about bosons? Well, that could be still interesting. And turned out thinking about bosons is still a very interesting problem, because we arrive at, what do you get out of bosons that have hard core? You get mod insulator or superfluid if you have bosons, hardcore bosons on a bipartite lattice, and that is kind of well known. But with this setting, we found that we get a very new type of state that is gapless. And that's something we're pursuing, trying to understand at least quantum bosons with trimer or cluster charging interactions. Another direction that we're pursuing is asking, coming back to my very beginning statement of how can you get fractionalization and sort of contrasting to the fractional Chern insulator. We are asking, can we consider effect of hopping? May not be a nearest neighbor hopping, but effect of hopping in a way that can get us to a fractional Chern insulator. What that would have to do to the spectrum of my many-body eigenstates is, without any hopping, my eigenstates were such that my spectrum, many-body spectrum, was that I had extensive degeneracy in the ground state. If I have Chern insulator, fractional Chern insulator, I should have just 3 states in the ground state. So that degeneracy, if I manage to go from my trimer state to a fractional Chern insulator, the spectrum will have to evolve from having this degenerate set of states to many of them lifting away and just 3 remaining. And we have some preliminary evidence that such transition can occur in a model that we are studying. But both of these are sort of at the moment rather preliminary, and I know this is being recorded and it's going to stay forever. So in case there is a mistake in the calculation, I didn't want to go further. But at this point, I think this is a good moment to end the talk. So I'm going to end with a summary. So the summary can be very simply stated. Okay. I told to some people, I like to be able to include something in my talk that I can talk to my kids about, because they're kind of casualties of me coming and having fun. So these are equations that both of my kids, I think, can understand. 3 unequal to 2 means trimers are quite different from dimers. And 3 is greater than 2. Physics of trimers are richer. And it's also a natural way to think about charge order in twisted bilayer graphene without being restricted to magic angle. And the final one that is, perhaps, I don't know, maybe it's more sophisticated, less sophisticated, but at least it's an equality, so it's an equation. So 3 minus 1 equals to 2 says 3 colored monomers are bionic. They are charged under 2 coupled Yuan gauge fields. So with that, thank you for your attention.
The Q&A section, if you have any questions.
Yes.
In the classical model, if we can draw like classical energy spectrum, is the energy between different competing phases like relatively degenerate?
So at exactly solvable point, there are infinitely many configurations that all have 0 energy. But away from the exactly solvable point, we have, so So away from the exactly solvable point, there are different phases. Sometimes they're degenerate, sometimes they're not. So let's see. Sorry, I don't like doing this, but I think that would be fastest. Okay, there. Oh, there's a phase diagram. So over here, I have √3 by √3 order. So that's a charge order. And there are 3 registries. If you have a finite size system, you have an edge. So you can say, where does my charge order start? And this side is the brick wall phase. In the brick wall phase, if I put the dots and look at, so if I connect the dots, I get a brick wall pattern, brick kind of laying out pattern. And there are 2 slants that you can give so that there's additional degeneracy. But each of those configurations have exactly the same energy.
Energy gap between the potential candidates of different configurations.
Energy gap between.
Try those, like for example, the brick wall configurations in the fluid phases. We can get the energy differences between.
Yes, right.
Or relatively large.
Well, I mean, so that's what gives, so right here, brick wall has the lower energy than √3 by √3 because, right? And the gap will depend on the interaction strength, J4 and U. Those are our 2 interaction strengths. I don't know if that answers your question.
Relatively competing, like the energy.
How competing they are more competing when you come here. That's why it's hard down here.
But it'll become larger. The gap will become larger in the.
Of course, yes, it gets larger when my scales get larger. Yes. Any other question? Yes.
So again, mapping from the trimer model to 3 dimer models, is that mapping 1-to-1?
It's not exactly 1-to-1.
So then, how does is there some constraint which is added in the timer picture?
So it seems that it is a good way to get to the long wavelength effective theory of like getting this exponent and so on. But the dimer model does not capture everything microscopically. Yeah. But our initial goal was to get the exponents. And at that level, it seems to be getting the right answer. Yeah. Yes?
Has there been any attempt to measure these phases in TPG, like at this third filling or something like that?
Right. So how would you measure these exponents? That's the question, right? Good question. I've been asking myself that too. So I don't know whether one can measure this in TBG per se. Like, okay, so how would you measure the density correlation function? You can do X-ray that would measure spectral function, but X-ray coupling to electron would only show me trimer correlation function. So the trimer correlation function with the pinch point structure would be sort of the most accessible thing if I consider X-ray. But these TBGs are thin flakes, so cannot really do X-ray with them. But so this pinch point has been observed in spin ices. So spin ice is a bulk 3D material which has this emergent photon. And it's the same story because there is a Gauss law associated with the ice rule. And the fact that Gauss law is in action can be observed through neutron scattering, showing you the pinch point structure. So that's sort of closest to what one can observe. We are hopeful that, oh, that's right. There is something that I didn't quite get to, which is I've been advertising our trimer, the cluster charging model is a little bit like, starting point or mother of many different kind of interesting phases. And as we think about different perturbation beyond what we've considered, you can get to models with rank 2 gauge theory, giving fractons and so on. And some of these things I think might be reachable in sort of Rydberg or cold atom kind of setting. And there you have different probes and different way of studying things. But it would be really cool to observe these fractional charge. And perhaps they are there, and it's just a matter of doing STM, but I don't think anybody has seen it yet. The best it comes to observing something close is in TBGs, people finding insulating phases at 1/3 fillings. So that's been actually quite robustly seen in many different settings. 1/3 insulating phase. Yep. Any other questions? Yes.
Thank you. Like this last slide, I think you showed with the infinity operator. Can you?
Landscape operator, yeah.
Does it have like a dual? Can you get a quantum code out of this?
Quantum code
Yeah.
out of this? Maybe. We're studying this. There are some cool things happening, but yeah. That would be an interesting direction. Yeah. I don't know the answer yet. Yeah. Duncan, yes. Is there any quantum Hall connection?
Something we kind of.
Right, you need something chiral to get to quantum Hall, right? Yeah. We are actually trying that. So actually,
Fractional phase, which
Yeah,
has
yeah.
nothing to do with fractional quantum.
so this actually, I'm really glad you're here and you asked that question because, remember in Washington, your talk, when we were in Washington University, in your talk, you quoted Titus's work, right? So after your talk, I got in touch with Titus and we are doing ED together. And we're finding if we use Haldane hopping together with our cluster charging interaction, you can go between fractional churn insulator and our cluster charging infinitely degenerate ground state. So what you see when you do ED is without the hopping, we have our extended degeneracy. That's like boom, 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 boom. I have all this like manifold of many states. And I turn on hopping, Haldane hopping, which gives me the time reversal symmetry breaking. They kind of all move up and only 3 remains and gives me a fractional churn insulator. And it's just really pretty. That's something that we're working on right now.
Fractionalization is before the.
Yeah, you can, yeah, exactly.
With quantum Hall, exactly. It's.
Right, yeah. Yeah, exactly. Yeah, it's kind of a different way to get to fractionalization, I think. So we're very excited about that. Any other questions? All right.
If there's no more questions,